Well, today we are coming to the last two lectures of the course, and what I'd like to do is to touch upon a topic that I really don't know very well. But I think it's important enough that I'm taking the risk of teaching something that I hardly understand, because I think that in the coming years we will see a lot of this topic, and you will be definitely encountering it in one way or the other. And the topic basically is organics or polymers that are used for electronics. Even though today the world of electronics revolves around the silicon chip, the day is not too far away when we will see significant changes in that world of electronics, where you will talk of, say, for example, displays that can be folded like a piece of paper and put in your pocket. Already that has been demonstrated. Circuits that are based completely on organic materials. Transistors have been demonstrated. Solar cells that use organic materials for functioning. So there's a whole range of things that's coming up that is very revolutionary and is fundamentally based on polymers and other organic molecules, small molecules and things like that. So that's why I'm going to take that risk of exposing you to it, not necessarily leaving you with a proper understanding, but at least some exposure to the topic, and then we'll leave it at that. And as you see the world unfold before you in this area, you grab what you think is important in the coming years. But I think you will see it in increasing measure. So let's begin with polymers for electronics. And what I'll do today is to try to go over a quick review of what are polymers like, how are they made, or what are the reactions that are involved, the basic properties of why polymers conduct, and so on. And then in the next lecture, what I'd like to give you is sort of little clippings of the state of the art for different types of devices, like displays that are based on organics, transistor technology, some little snippets of where organics are going currently. So today's will be more like a broader review on polymers in general, with a little bit about how they conduct and some of the problems related to polymers in electronics. When we use the word polymer, what are we talking about? Basically, they're commonly, one of the common names that is given is plastics, though not strictly speaking, that's not the best definition. But when we talk of polymers, one of the first things our minds go to is plastics that we use in everyday life. But the word polymer consists of two words, poly and mer. And the idea of the word mer is like a unit, a smaller unit of something. And what we have is, when we use the word polymer, is a bunch of those units strung together. There's another word that we will make use of called monomer. Basically, it refers to the building block, that structural unit, that one unit that is then multiplied many times to give you a polymer. And these are broadly organic materials, in that most of them consist of a chain of carbon atoms with various things linked to it. But there are also inorganic polymers, and we will not go into that other than just to give you an example. We can talk of various silicones and some silicates, SiO kind of bonds, where they form polymers, which are inorganic polymers. But fundamentally, the ones that we will deal with in this class are organic polymers. Another term that is used incidentally for polymer is also macromolecule. The idea, macro, large, and so something that is a large molecule, large molecular weight materials. Here's an example of ethylene. You know this compound, C2H4, which has the following structure, with a double bond in the middle. That's one of the important things. This is the monomer, and out of this we fabricate the polymer. N of these monomers combine together to produce the polymer, and we use that notation. These are the monomers, N of them combining to produce a polymer. Actually, there will be, I'm not very sure of these notations myself, but some idea, something like, the idea being that you've got N of these, there's a, okay, basically the bonding will be that the double bond breaks up, and you have now a system like this. I don't remember the exact notation there, but it's N as a subscript, indicating that they're all coupled together. So the double bond is broken up, and I've got now 2 single bonds on either side. And now you can go on adding a chain. The next molecule comes here. There also the double bond is broken up and coupled here, and so on. So this sequence will give us polyethylene. That was ethylene, and that's polyethylene, very common polymer that we use. There's another example in this family itself. What if I substitute, instead of this H, I make a substitution and I put in one chlorine atom. So we've got now C2H3Cl, vinyl chloride or vinyl chloride. Okay? And so you can imagine then that the polymer of that will be called polyvinyl chloride or PVC. We use the term PVC all the time. What is that? It is basically this kind, the same as for ethylene, except that now one of them had been substituted with chlorine. Now you're going to break these double bonds in the polymer, and you'll get then a chain of these. So this substitution was made instead of this hydrogen. You can do the same again and create polystyrene, where essentially now you have the same structure, except that a benzene ring has been substituted instead of one of the hydrogens. Just like the ethylene molecule, you've gone and put in a benzene ring instead of one of the hydrogens, and you get polystyrene. Styrofoam, all those words we use, that's related to this. Now, if the chain ends are left like this, that chain will not be very stable. So there's something on either end of the chain typically for any of these, whatever we have, some sequence like this, and the chain is terminated on either end by some molecule. Could be an atom or a radical. And what that does is terminate the 2 ends. There's always these free ones that can go on adding. And these atoms or radicals are known as initiators. Okay, so you can have OH. Chlorine is another example. You can have chlorine molecules on either end, and so on. So this is the way the chain forms, but ends of the chains are sort of capped off with one of these initiator atoms or radicals. Now, when we talk about a material like a polymer like this, we are used to describing molecular weight. And for most of the compounds we are familiar with, there's no problem with that concept. If I've got H2O, what is the molecular weight? 18. There's no problem with that. But I show you polyethylene, and I ask you what is the molecular weight of polyethylene, which was what? C2H4N. It's very difficult to describe. What is the molecular weight? The problem is not all the chains in a polyethylene solid have the same N value. All right? One chain had, let's say, 1,000 of them coupled together. Another one has got 1,500. Another may have 900. So how do we define its molecular weight? So when we talk of the molecular weight, there are different definitions there. But in general, we're talking of some average value for the number of these that have coupled together times the molecular weight of C2H4. So that's how we will describe it. Another way to talk about is the degree of polymerization. Incidentally, an average value for polyethylene could be about 25,000. Right? We just saw H2O is 18. By comparison, an average value for polyethylene could be something as high as 25,000. So they're very different, and that's the idea of a macromolecule, huge molecular weights, and accordingly properties are different, and there's a distribution of these weights. Anyway, we come to degree of polymerization, dP, and basically what is the average N value? I said that N varies, and so when we talk of degree of polymerization, we are asking the question, what is the average value of N? And so in this particular case, N would be equal to the molecular weight of C2H4N by the molecular weight of C2H4. Okay? So the average molecular weight of C2H4N divided by the molecular weight of C2H4. So to use this illustration of our polyethylene, PE, the average molecular weight, I said, let's say, is 25,000. The weight of molecule of C2H4 is 24 plus 4, roughly. You can put in the exact values there. That's 28. You get something like 890, somewhere around that number. So the degree of polymerization of a polyethylene with average molecular weight of 25,000 is about 890. That means 890 monomers are coupled together on an average to form this particular sample of polyethylene. Now, it could be something different in another case, but this is just an example. Polymers can also be classified as thermoplastic and thermosetting. Depending on how they behave when they are heated up. Thermoplastics, for example, are soft, they soften and deform upon heating. And this process is reversible. You cool it down, it hardens. You heat it up, it softens. That's the one that we commonly call plastics. You know, most of the plastics, you heat it up, many of them, I would say, we find it softening, and that's why we can't use plastic buckets to put very hot water. We may end up with the bucket itself just melting and things like that, or at least it softens. You put a container near the flame too close, you find that it's softened, and so on. And this process is reversible. When it's hardened, when it's cooled down, it hardens. And this is a characteristic of what are called linear polymers, which I'll illustrate in a second. So many of the common ones that we just looked like PE, polyethylene, PVC, polyvinyl chloride, these are called linear polymers, and we'll see. They behave in this thermoplastic fashion. Then looking at the thermosetting ones, they actually harden and become rigid upon cooling, upon heating, and then it's not a reversible process. So they harden and become rigid upon heating. They set, that's why they're called thermosetting. When you heat them up, they set like concrete. You know, it's called setting of concrete, setting of cements. And there are similar ideas involved there. Bonds are being created during the heating process that causes the material to become far more rigid than it was. It's a non-reversible process. And this is a characteristic of network polymers. Okay. The previous case, thermoplastic, we saw was a characteristic of linear polymers. This is a characteristic of network polymers. Here's an example. The formation of phenol formaldehyde resin, which is also known as bakelite. We start with phenol, two phenols, which are low melting point solid. And we add formaldehyde, which is a gas. And what we produce is this polymer phenol formaldehyde. I will come to that in a second, the details of it. But this is the basic bakelite, I'll put it there. when you heat it up, it hardens. Okay. In general, the polymers, the properties are variable depending on the particular structure. So the same polymer molecule could have different structures. Isomers. They have the same chemical formula, different structures. It depends also on the molecular weight. As we saw sample to sample, the average molecular weight could change. So the properties that we are interested in could vary depending on the particular structure we are looking at and the average molecular weight and so on. Now it's possible also to create sort of alloys, the equivalent of alloys. We take one metal in metal world and mix it with another to create an alloy. You can also create polymer blends. Two polymers that you can combine together to blend it. Incidentally, the example that I gave here of taking phenol and formaldehyde is what the formation is of this is what is known as a copolymer. The two components are not the same. Remember, for polyethylene and all that, we took two ethylene molecules and combined it. They were identical and we got polyethylene. Here we are taking two different things and combining it to form the polymer. In that case, it's a copolymer. Whereas our blend is sort of the equivalent to the polymer world of what we have in metals as alloys. Now, we are not simply stuck with using these things. We can still modify polymers, put in all kinds of other atoms in there that give it other properties, make it more reactive, make it less reactive, and so on. But in order to process polymers, we are also going to use some other things, some additives. These are various things that are used to either change the properties or make it more processable. And one we already saw, the initiator. We said we need either some termination group like OH or Cl or something like that. Another would be a catalyst. Many of these reactions require some energy, and they proceed at lower energies and things like at lower temperatures if you have a catalyst. And so various catalysts are used which accelerate the process, and so they are also known as accelerators or hardeners. Okay? They speed up the process. And then we can have plasticizers, which correspondingly, instead of hardening, softens the polymer. It's something is added to make it a little bit more processable, so it's more plastic. So it's also a softener. And examples of that are certain resins, organic solvents, in some cases even water. And then you have stabilizers. These are materials that prevent the degradation or the deterioration of the polymer on exposure to the environment or so on. Because many of them will deteriorate with time, and you want to make the plastic more stable, you put in stabilizers which prevent deterioration or degradation. Then you would have something very important, fillers. As the name implies, they're used in large quantities to fill. So they give mechanical strength, and they fill up, they take up the bulk of the polymer. It's added in fairly large quantities, and examples involve mica, wood fiber, glass fibers, and something very interesting I saw, flour. Okay, that's also used as a filler in some cases. I don't know, wheat or something like that. Pardon? Any? Yeah, probably. I mean, it's not natural fiber is in there in these. There are various proteins and things like that, and they would add bulk to the polymer. They're just filling up, and they make it stronger. And then you have, in certain cases, flame retardants. Can you think of an application where in the polymer the flame retardant would be there? That means it doesn't catch fire very easily or burn very easily.
We have that spray cooking utensils.
Like a Teflon coating? Okay. That usually you don't need a flame retardant because the metal will be on the bottom and the Teflon will be on the top.
Polymer paints are there. We may use that the flame retardant in that case, so that the paint doesn't
Catch fire. Okay. A very common use is in these cable coatings. You see, when you've got electrical wires, you've got plastic covering on it. And if there is a short circuit, then that flame is going to propagate through the walls all over the place. So one common application is to use flame retardant cables, special cables. You see various companies nowadays advertising that it's available in India. Anchor or somebody, they've got a special grade of cable which is flame retardant. It prevents the propagation of the fire when there's a short circuit, for example. Very critical because many accidents occur that way. And then another one, common one, colorants. Make the plastics very colorful. Polymers are very colorful things. You can add all kinds of pigments, which are typically insoluble, or dyes, which are soluble organics. So these are different kinds of additives that are used in a polymer to make it, to give it different properties or to change its properties or to make it cheaper, more colorful and so on. I'll define another term here for us called functionality of polymers. And we'll see that basically to form the polymer from the monomer, we need a certain degree of functionality. What it is, we'll see in a second. If we have a monomer and it needs to grow, it can grow if some function is available. At least two sites are available, we'll see. Two reaction sites. Function means some site where it can react. I should say if some function available, basically those are at least two reaction sites. What do I mean by that? I'll illustrate in a second. Take the example of our ethylene molecule again. C2H4. Because of the presence of the double bond, the double bond can break up, giving me two reaction points. This monomer has got bifunctionality. Okay? And for a monomer to grow, there should be at least one double bond. That means at least it should have bifunctionality. There are monomers which have got three reaction sites, and then we'll call them trifunctional. If they have four, they are called tetrafunctional. More than four creates problems because of space constraints. It's not possible for the monomer to grow. And so typically you have either, you need for a monomer to grow into a polymer, at least one double bond, that is a bifunctional monomer, or you may have trifunctional or tetrafunctional monomers. I already illustrated what I'm going to say right now, but I'll give you some specific terms for it, namely the mechanisms by which polymers form. And we looked at two examples. The two basic mechanisms, one is known as addition polymerization, or it is also known as chain reaction polymerization. Okay. And the example of that was again the classic ethylene or PVC or whatever we want of that kind. We get our polymer. The important thing here is that one monomer added to another monomer, no byproduct. I took two monomers, I got the polymer. There's nothing else that is formed over there. And some energy is required in some form, either in the form of heat or as a catalyst or something to initiate this reaction. The second mechanism is known as condensation or step reaction polymerization. And we already looked at this example of phenol formaldehyde formation. And I'll give that a little more in detail here. The important difference between condensation and addition polymerization is that here we have some byproduct formation. And the byproduct could be a water molecule, okay, methanol, HCl, etc. Some byproduct is formed when we combine two of these together. Let's go back and look at phenol formaldehyde. Phenol is basically this structure. We've got the benzene ring, and we have H, and one OH here. When we take two phenols, the same thing, and we add formaldehyde to it. Formaldehyde has the formula CH2. Okay, CH. I mean HCH, the same thing. So we have C, H2, and then we have O, right? HCHO for a second. That was wondering. No, I thought of something different, and then I realized it's the same thing you're talking about. And what we see here is that when we add the formaldehyde, a water molecule condenses out of there. So phenol plus formaldehyde gives me phenol formaldehyde, which is going to look the same as the phenol with the CH2 stuck in there. So I got OH, H, and then we have H, C, and I'm not drawing the rest. You got the other molecule there. So instead of these two H atoms that were there, we've now got it bonded through a carbon there. Plus the byproduct water. Okay, the same molecule here will be drawn out here. I just didn't bother to draw that. So this is an example of condensation polymerization with the elimination of a water molecule. As I also mentioned, this is an example of copolymerization. We've got different types of things involved in there rather than the same monomers. Second phenol molecule. This is one, this is another. I didn't draw it, you can draw it. The same thing, just like that. Why not?
The carbons separately.
Oh, here you mean the C will be attached to
that
it.
H bond.
Let's see, 2 carbons, 3, 2, 3, 4 are there.
That H will be printed. Sir, that H will be removed out and the carbon will be attached to the carbon.
Yeah, but will that, oh I see. Otherwise carbon doesn't have 4 valency, you're very right. Carbon should have 4 valency. This way we have 2 H's here. Yeah, 1, 2, so we'll get the 4 valency. Otherwise, you're right. Valency would not be satisfied. Okay? Is that satisfied now? 1, 2, 3, 4, yeah. Okay, thank you. So that's the phenol formaldehyde formation. I mentioned the word linear polymers and I mentioned the word network polymers, and we'll look at the classification of polymers based on their structure for a second. Linear polymers we have looked at have long chains that are not so intertwined. You can separate them from each other. Okay. We have strong bonding within the chain. So these are all covalent bonds that are forming part of the polymer. But we have weak van der Waals bonding between the chains. And as a result, it's easy for these chains to slip with respect to each other. They melt on heating. And many of the bifunctional polymers exhibit this behavior. So it will look something like this, long chains that are not very intertwined, which we can separate out. Textile fibers and so on have this kind of a structure. The second class that I mentioned are called framework or network polymers. And these are in general formed by trifunctional and tetrafunctional monomers. As the name implies, there is a network that is formed, and as a result, the material has got a higher melting point. You have to break a lot more of bonds for this thing to move. So it's got a higher melting point, it's stronger, more rigid, and so it may look something like this. I'm just going to draw some arbitrary network. Okay. There's a three-dimensional network, and that's what makes it strong and rigid. You've got another category, what are known as the cross-linked chain. Here also we've got long chains, but they are cross-linked properly. So we've again got longer chains, except there's good linking between these chains. Okay, so they are not weak bonds there, they are fairly strongly bonded between the chains by these cross-links. The chains are cross-linked and therefore cannot move easily. So we've got more rigidity. Than the linear polymers. An example of this is, say, vulcanizing with sulfur. Yeah, hey, he knows it. When you take rubber and you vulcanize it with sulfur, you produce cross-links that are used to form a more rigid structure. The next category is what is known as branched chain polymer. And these are generally thermoplastic. And there are different kinds of side chains. Let's say there's a main backbone, and we may have side chains that go off of the main backbone. Now these chains could be of different lengths. The chains don't have to be identical to each other or to the main backbone. Okay, so that's they are also very mechanically strong. Sort of more like a spread out tendrils like that. And then one other classification is as crystalline polymers. Normally we think of polymers as being amorphous, but polymers could be crystalline, though almost never will they be fully crystalline. So they range in structure from being amorphous to partially crystalline. And it's usually the linear kinds of molecules that tend to be more crystalline. That's a quick run through of the classification of polymers and reactions that are involved in forming them and so on. We come to the part that is of greater essence to us, namely the electrical conduction behavior of polymers. We're already familiar to some extent with the electrical behavior of polymers. We know that they can be used as insulators. There's no problem in understanding that, because all the time we utilize it in that form, plastics that are used in different form as electrical insulators. And in the previous topic that we were looking at, namely dielectric materials, we also saw that there are polymers that could behave as dielectrics. Do you remember an example? That was only about a lecture ago, or 2 lectures at most. Polystyrene. We saw its properties in comparison with a high K dielectric. Yeah? And we saw that it's mostly electronic bond polarization versus for high K dielectrics, ionic shift that is there. Already forgotten. That's only 2 lectures ago, or 1 lecture ago. Anyway, polymers there can also, because of their properties as dielectrics, be used in dielectric material as a dielectric material. But what is very surprising is that under certain conditions they function as conductors, and actually some of them even function as superconductors. So what we have here is that depending on their structure and the way we treat them and so on, we could make polymers that span the whole range of conductivity. I'm going to give you a graph just to illustrate my point here. If we make a comparison between organic polymers and inorganic materials that are there in terms of conductivity, sigma, with units of Siemens per centimeter. And on one side I will list, okay, let's put the conduction value here. I'll list some of the inorganic materials that are used over this range. So down here would be, say, our insulator category. We're talking of something like less than 10 to the power minus 15 conductivity, very insulating. And we're talking of a material like silica. In the organic world, it has a counterpart, Teflon. Okay? Very insulating. And then when you go a little higher, you've got nylon. And then about 10 to the power minus 13, we've got polyacetylene in a particular form known as the cis form. This is one of the isomers. And then there's others. We'll come up to about, in the interest of time, 10 to the power minus 7. We've got the other form of polyacetylene called the trans polyacetylene. And then at about 10 to the power minus 5, we've got a material on the inorganic side like boron. Many of the typical semiconductors we're talking of 10 to the power minus 1 to 10 to the power 3 in that 10 to the power 2 range. So many of the semiconductors are somewhere here. And then you've got metals out here, bismuth, copper, and then way up higher, the superconductors. So we're talking of about 10 to the power 5 at that point there. It's interesting that doped polyacetylene, this is undoped, doped polyacetylene has been found to have as high as this range. So what do we see? It's behaving like a metal practically. The corresponding inorganic side, we're talking of conductivities somewhere near copper. Undoped, depending on the particular form, it's either cis or trans. It's 10 to the power minus 13 or 10 to the power minus 7. You dope it, there is a radical change in this. In fact, it is in this field of conducting polymers that the Nobel Prize was awarded in year 2000 for chemistry. And it has made a big revolution, not the Nobel Prize, but this discovery of conducting polymers has really dramatically changed because they are so easy to handle relative to the regular semiconductors. And we'll look at some of those effects in a second. So this is the broad idea of the conductivity in comparison with inorganic materials. Here are some of the great, the reason why it is so useful, the advantages. All right, late 70s onwards, this has been developing. First of all, ion transport is possible. You can have various ions attached to this, and so ion transport is possible in addition to electronic transport. Electrochemical effects have been studied, so you can use its electrochemistry. It has been shown to demonstrate photoactivity, namely change in property with light, exposure to light. It has catalytic properties. So you can think of, say, for sensor behavior, it catalyzes something, and so we see a change in its behavior. Junction effects have been demonstrated. Very critical if you want to have something like a p-n junction or a transistor and so on. So these are the different effects that have been seen and demonstrated in polymers. In addition, you have lightweight, flexibility, non-metallic surface properties, and other physical properties that are related to the polymer behavior. And here are some of the key words: flexible, light, and there's another one, cheap. Easy to process. You can use something as simple as a spin coater. You know what's a spin coater? There's a spinning wheel at high RPM. You put your material on which you want to coat your polymer. In a liquid form, you drop it on there. At high RPM, it spins. Centrifugal forces create a thin film on it. There you have it. And imagine, compared with that, how a semiconductor crystal is grown and produced ultimately in the form of a chip. The complexity that is involved. Much simpler to work with these. Not very well understood. There are other problems, but still, in terms of processing and cost and so on, it is orders of magnitude different compared. And that's what makes me worried, because I work with semiconductors, which will soon maybe get a little outdated if the polymer people have their way. So I'll just give you a list, a rough list of where all these kind of things. We already saw dielectrics and insulators. And so here are some of the other application areas that people have already started using it or are considering using it. For battery electrodes, there's already batteries out there in the market that make use of polymers. It's got a polymer in it. Okay. Sensors. Switchable membranes. Just a quick list. We'll look at some of these in more details later. Display systems. Optoelectronic devices. Excuse me. Information storage. If it's a dielectric, you can think of it as similar to being used for a memory device. Now, depending on the kind of polymer you use and what all functional groups are attached to it, bioactive systems or biocompatible systems. A lot of our body consists of organic materials, and so if you can have devices that are compatible with our body, that would be great. Okay? So this is just a broad listing of the kind. There's many more, but just to give a flavor for where people foresee going with this. I don't have much time left in this class. I'd hope to finish a lot more, but I'll begin with conducting polymers. There's two categories, broad categories of conducting polymers. There's polyacetylene, which was, I think, first studied and best defined, well understood class of polymers. We use the word here, conjugated polymer, and in that sense it is the simplest conjugated polymer. I'll give you what a conjugated polymer is in a second. A conjugated polymer, the best I understand it, consists of alternating single double bonds. Okay? And somehow that seems to be the key to the behavior of conducting polymers, the presence of alternating single double bonds. Pi electron formation, delocalized pi electrons is something they call it. So this is the simplest in that category, which we have, is polyacetylene. There's another class called polypherols, which are also in the category of heteroaromatic polymers. These are more stable, though polyacetylene has been really studied and is well understood. But polypherols are becoming more popular. They are more stable, easy to prepare, and because of their structure, there is greater opportunity to functionalize. We can do a lot more with this category of polymers. Attach all kinds of other groups that will change the properties. Take the basic molecule, change part of it, attach a different functional group by reactions, and you can get different properties out of the polypherols. We'll look at polyacetylene particularly, and as I mentioned, there's two isomers of polyacetylene. One is called the cis polyacetylene. I'm using PA as an abbreviation there, which basically consists of the following structure. And what we'll see here is, in this case, the hydrogen that is bonded is on the same side of the double bond. Both these hydrogens are on the same side there. Here they're down here, sorry, hydrogen, hydrogen, again they're up there. I'm not drawing the angles right, but just giving an idea. Okay? And then we have trans polyacetylene, where the structure looks somewhat like this. And here we have the hydrogen getting attached on both sides of this double bond. And so on. These are the two basic types that are there. And as you will have noticed, cis was the one that had the lower conductivity. Trans was the one that had the higher conductivity in the undoped state. And now we can take this and dope it to get different properties. This had, cis had the 10 to the power minus 13 Siemens per centimeter. And this was something like 10 to the power minus 7 Siemens per centimeter in the undoped state. So there's a big difference between these two. The cis isomer is a low temperature isomer. It is obtained at lower temperatures, minus 77 degrees centigrade or so. This is at relatively high temperatures, 170 degrees centigrade. So the particular isomer that is formed depends on what temperature you're processing at and so on. And the properties of these are very, very different. we will take these and we'll dope it, and we'll see that once it is doped, we do not have two isomers anymore. In the doped form, it is always going to be one of these isomers, not cis and trans separately. I'll introduce the concept of a soliton, and we'll close with that. Note that the trans isomer has got twofold degeneracy. What do I mean by that? We can either write it this way, the way I've written it, or I could write it the opposite way, this one. Right? What happens when we bring two of these next to each other? There will be places where two single bonds will come together. Unsatisfied valency. So if I attach this one to this end here, I'm going to get, let's see, I draw it properly again. Here we got this one here, and then I attach it here. Out here is what is called a soliton. And solitons are formed only in this acetylene. There are other mechanisms known as polarons, which we will see later, which are found in other materials. But the soliton formation, and if we continue this process and add on another one, we'll get another soliton. The mirror image of a soliton is known as an anti-soliton. Okay, so we'll create a soliton-anti-soliton pair if we add on another one on the other side. And fundamentally, you may think of a soliton like some kind of a defect level in the band gap. If you think of polyacetylene having a band structure, there's a band gap. What the soliton formation does is to introduce like a shallow level in there. And so you can excite out of it and so on using semiconductor terminology and create conduction. Rather than exciting across the band gap, you're exciting from a shallow level, as if it's like an N-type defect. N-type dopant. And that's how the soliton mechanism, or the other thing is the soliton may move. You see, it's a double single. So if this flips here, then that becomes the single one. And so you got the soliton has moved here. And so a soliton wave can be created. That could be thought of as if an electron is moving. It's a charge transfer. So the soliton plays a fundamental role in the behavior of polyacetylene as a conductor. I'll take that up more in detail next time, a little more, clearer definition of a soliton, and some more properties of when we dope, when we meet the next time.